Okay, so we left off last time with the combined gas law that allowed us to see how a system's volume, pressure, and temperature are related to each other, and how changes in, say, the pressure and temperature could give us the change in the volume that we would expect. And that was kind of a combination of Boyle's law and Charles's law together. There was a new law, Avogadro's law, and I think we may have covered that, but I'm just going to review it really quickly just in case. Avogadro's law, first of all those previous laws all had to do with gas samples that had a constant number of moles of particles. In other words, if you're a balloon or piston or whatever vessel you're holding your gases in, it must have no leaks. There must not be any gas particles escaping or entering for those combined gas laws to hold true, and that seems pretty reasonable. Avogadro's law then said that the volume was proportional to n, the number of moles of gas particles, and that's keeping temperature and pressure constant now. And so we could summarize this as V1 over N1 is equal to V2 over N2. And if I, say, doubled the amount of gas particles in my system, keeping temperature and pressure constant, then the volume would double as well, is what Avogadro's law said. And it seems maybe not very profound, but it was actually the last piece to the puzzle for moving to what we call the ideal gas law, which took gases and which took the combined gas laws and provided a bridge or a connection to the microscopic model for how gases behave. And so until now we've known that PV over T is equal to some constant, and that's the combined gas law. And that constant would be the same for a given gas sample under different pressure, volume, and temperature conditions. And so we could use that combined gas law as those conditions change, but it would be a different constant for, say, nitrogen versus oxygen if you had the same mass of gas, or if you had two different oxygen gas samples, but one of them had twice the mass of the other. And so this constant was sort of particular to your experiment, to the exact type and amount of gas that you were using. However, when you added Avogadro's law in here, then you would have PV over NT is equal to a constant. And as long as you knew your number of moles, it turned out that the constant was the same for every sample. Doesn't matter if it's carbon dioxide or helium. Doesn't matter if you have 10 kilograms of gas or 3 micrograms. They were always equal to the same constant. And so we gave that constant a name, the gas constant. And it's represented with a capital letter R. And the gas constant actually is a really fundamental value that will turn up later in this course in other circumstances that have nothing to do with gases at all. So it's a very interesting number. But all you need to know for now is that while the gas constant can take different values and different units depending on its context, in the gas laws that we're talking about, R is equal to 0.08206 liters atmospheres per mole Kelvin. And you'll notice those units match, atmospheres for the pressure, liters for the volume, moles for N, and Kelvin for the temperature. So this number is one that's worth memorizing. It'll come up a lot. Now that we had the ideal gas law, we could talk about not just the volume that a particular sample of gas would occupy compared to its previous conditions, but we could talk about gases generally. And it became convenient to define standard temperature and pressure so that we could compare gases, their densities and such. And so standard temperature is 0 degrees Celsius. And we'll often use 25 degrees Celsius in problems because that's like an average room temperature. It's more convenient, I guess, for actual laboratory example problems. But the standard temperature is defined as 0 degrees Celsius. And then standard pressure is precisely 1 atmosphere of pressure. And at standard temperature and pressure, 1 mole of gas is going to equal 22.4 liters of volume. So that's a good number. You don't need to memorize that, but I think it's a good number to kind of be vaguely aware of, that 1 mole of gas is about 20 liters under ordinary pressures and temperatures. Our lower atmospheric pressure in Cedar City would increase that number by a fair amount, but at 0 degrees Celsius and 1 atmosphere, exactly 1 mole of gas would occupy 22.4 liters. So if we come back here, we can erase all that, and I'll leave R up there, just because it'll be useful to us later. It's easiest to remember the relationships between pressure, volume, number of moles, temperature, and the gas constant by rearranging that ratio to be PV equals nRT. So sometimes people pronounce this as PIV-NERT, which seems to be fun to say and easy to remember. So PIV-NERT, or PV equals nRT, is the ideal gas law. Then I say that the ideal gas law is called ideal not because it's better than other gas laws, but rather because it is the law which describes the behavior of an ideal gas, the behavior of a gas which perfectly obeys those 5 postulates of the kinetic molecular theory of gases. So there are more complicated gas laws that are objectively better than the ideal gas law, that try to take into account the ways that real gases will deviate away from those 5 idealized postulates of the kinetic molecular theory of gases. So that's what we mean by ideal when we say the ideal gas law, is that it is a simplified law based on a very idealized model. And so we can use the ideal gas law to solve, different types of problems. If we wanted to find the pressure of a gas sample with 0.25 moles occupying a volume of 5.2 liters and 15 degrees Celsius, then what we would do is say PV equals nRT. Let's rearrange that to P equals nRT over V. And so P is going to equal 0.250 moles times that ideal gas, that gas constant, 0.08206 liters atmospheres per mole Kelvin, times the temperature, and 15 degrees Celsius would be 288.15 Kelvin, divided by that volume of 5.20 liters. This would give us a pressure equal to 1.14 atmospheres. We could go the other way and figure out how many moles are in a sample. Sorry, I'm reading I'm reading from my laptop screen. If you're wondering why I'm bending over there. How many moles are in a 3.15 liter helium balloon at 20 degrees Celsius and 0.820 atmospheres? So if we wanted to solve for the number of moles, we'd say N is equal to PV over RT. So N, that would equal 0.82 atmospheres times volume of 3.15 liters over 0.08206 liters atmospheres per mole Kelvin. And that temperature, 20 degrees Celsius, is going to be 293.15 Kelvin. We must always convert our temperatures into Kelvin for gas law problems. And it looks like that will be 0.107 moles. I'll stand over here. So the ideal gas law allows us to take our macroscopic observable properties like pressure, temperature, and volume and relate them to a count of microscopic particles that make up the gas, which I hope you appreciate is kind of incredible. There's no way that we could count the particles in a helium balloon even if we had a microscope where we could see them. They'd be moving too fast. There's just too many. This is one way that we can actually arrive at an accurate accounting of the number of gas particles in a gas sample. Okay, there's one more little section I want to cover in this video, and that has to do with mixtures of gases. So the ideal gas law still doesn't distinguish between types of gas particles. So if I have 1 mole of helium or 1 mole of oxygen or 1 mole of nitrogen under the same temperature and pressure, they'll occupy the same volume. And so if I have a gas that is a mixture of gases, then its total pressure and temperature and volume just depend on the total number of gas particles, independent of what their chemical identity is. But we can also talk about how the total pressure is contributed to by a partial pressure from each of the different components that make up the mixture of gases. So this is called Dalton's law of partial pressures, and I'll write it up mathematically here. That says that the total pressure of a gas mixture is equal to the sum of the partial pressures. I'm sorry, those I's have, that's a little better. The sum of the partial pressures exerted by each of its individual components. And so the partial pressure of the individual component we can get from PV equals nRT, when we just consider N the number of moles of that component of the gas mixture. And this is called Dalton's law of partial pressures. Each gas will exert a partial pressure, as if the other gases in the mixture weren't even there. And then the total pressure will be the sum of the partial pressures exerted by each of the individual components within the gas mixture. So let me advance to our practice problem here. So the air is made up mostly of oxygen and nitrogen. Between those two, that's about 99% of our atmosphere. And so if in Cedar City, if the pressure of oxygen is equal to 0.17 atmospheres, and the pressure of nitrogen is equal to 0.64 atmospheres, then what can we expect the total pressure to be? Well, P total, for the atmosphere, which is a mixture of these two gases, is going to equal the sum of their individual partial pressures. In other words, 0.17 atmospheres plus 0.64 atmospheres. And this will equal 0.81 atmospheres, about an average barometric pressure for Cedar City. You dealt with partial pressures in your collection of hydrogen gas lab just before spring break, and so hopefully this is kind of almost a review for you, but that was a very typical application of Dalton's law of partial pressures, because we had to subtract off the pressure due to the water vapor in order to figure out the pressure that was the partial pressure that was exerted by the hydrogen alone before we could convert it into a number of moles. So I'll make another video for today in just a moment.